To wrap up Module 8, we're going to look at cholesterol, the most prominent steroid. Steroids are a class of lipids whose carbon skeletons are made up of fused rings. And so here's an example of how we can still number the carbons on a steroid molecule. This is good to see because, we can kind of imagine that it's a long fatty acid chain that's bent around. And this is to illustrate that it's not all that different from a fatty acid chain, but knowing the exact process of how this works isn't totally important, but to know that this is a class of lipids. And so the most important steroid that we're going to look at is cholesterol, and it has the following structure. Cholesterol gets kind of a bad rap in nutrition because it's associated with health effects, high cholesterol, but it is an essential compound, an essential molecule for creating other hormones, and understanding its role in the body is an important part of understanding biochemistry. Cholesterol is obtained in the diet from a lot of sources: meat, cheese, butter, eggs, etc. And as we're looking at cholesterol to begin with, go ahead and pause the video here and consider, is cholesterol water or fat soluble? All right, hopefully you've gotten to pause the video and think about this a little bit. We want to look at the structure of cholesterol and predict this really big top-level determinant of its behavior. And when we look at it, it's mostly nonpolar, right? There is an OH group there, and that's important, but for the most part, this is a lot of hydrocarbon. And when we see hydrocarbon, we want to think nonpolar. And so this is not water soluble. And a lot of times, when we look at a structure, we may not know exactly how is this really water soluble, really fat soluble, not water soluble, somewhat soluble. But in the lab, we can put it in water and see that it is not water soluble. And this structure here, I think, suggests pretty clearly that this is not going to be water soluble. Rest assured, we can confirm via testing that cholesterol is definitely not very water soluble at all. And so, if it's not water soluble, how is it transported around the body? And this is a challenge for all lipids, right? Because lipids are nonpolar. They don't want to just dissolve in blood and allow themselves to be transported around the body. So how do they get transported? Well, this is through lipoproteins, where we have these assemblies of phospholipids and other proteins that are containing the nonpolar lipids like triglycerides or even cholesterol, right? These are insoluble in the blood, and when we contain them in something that looks really very much like a micelle made up of phospholipids and other proteins, we are able to transport these non-water soluble substances around the body and get them to where they need to be, from where they're produced to where they need to be used, etc. And so when it comes to cholesterol, right, we have low density lipoproteins that transport cholesterol from the liver to the tissues, and high density lipoproteins that transport cholesterol from the tissues back to the liver. And one of the challenges of cholesterol is that when we have LDLs, these can deposit cholesterol on the walls of the arteries when there's too many of them, right? When they're carrying more that's needed to form cell membranes and do the functions, they have extras, they have leftovers. And these leftovers deposit on the walls of the arteries, which is obviously not good because it's going to restrict blood flow and things like that. This is your bad cholesterol, right? This is what you don't really want to have too much of, right? And associated with the high cholesterol and the health effects of your cholesterol. And we talk about the good cholesterol. This is what's bringing them back, right? This is reducing the overall bloodstream cholesterol level by bringing it back to the liver. And here are some recommended levels that we want to consider. Remember that we looked at levels of common, things that were, in our previous chapters, where we're looking at how to diagnose what's too high, what's too low, etc. We do have some drugs that are designed to reduce the levels of cholesterol. So here are statins, and here's a couple of examples of molecular formulas of these statins that are shown to reduce the levels of cholesterol. And this is good to have, right, because this is one way of treating things. But I think that when we have a drug like this that is just targeting the cholesterol, this could conceivably interfere with, some of the things that cholesterol is doing as well. Not all of this is always known completely. When we take a drug to trial, what we are showing when a drug is taken to trial is A, that it's effectively lowering the cholesterol, and B, that it's not overly harming people from a big picture thing, right? That people who take the statins aren't developing some sort of other ailment really quickly by taking the statins. That's sort of the big focuses of a drug trial, to show that a drug is safe and effective. However, no one has a crystal ball that investigates every single thing that drugs do when they're in biochemistry. And many drugs are found to have additional effects well beyond their use. And this comes in the form of off-label prescriptions, so maybe some good things are found, like this drug is doing even more than we originally thought. Or it could come in the form of unwanted side effects that just aren't shown until later. And I think this is important to remember, because cholesterol is an essential part of our body, right? Cholesterol, to illustrate, is a raw material for many essential steroid hormones. And we hear steroid with human growth hormones and like anabolic steroids, but steroid is just a class of molecules of which cholesterol is one, and which these other hormones that we've probably heard of are as well. And some of the ones that we've known, the most are like, testosterone, progesterone, but these are all created from cholesterol. Cholesterol is the raw material for creating these important hormones, which are also essential to have in balance. And when we look at these, I hope when you look at these different steroid hormones on the right, we can see some really strong similarities with the structure of cholesterol. Cholesterol is the raw material, and through biochemical processes, we can react the cholesterol into creating whatever hormones we need. Hormones as a class of molecules are often responsible for slow change in the body, right? When it comes to some signaling, we want really, really fast signaling. Hormones tend to be slower acting and more long lasting. They're an important class of molecules as well, and a lot of them stem from cholesterol.